Okay, this is the very last slide for the initial part. Essentially, the impact of Internet of Energy is potentially terrific, because after 1 century of stability, because for 1 century the electrical market has been working more or less with the same rules, now we are approaching a bottom-up revolution. It's not a top-down revolution, it's a bottom-up, because it will be the end users that will put their money and the resources necessary to develop this innovation. And the pressure is, of course, done by environmental needs, limits of the conventional infrastructure. This has to be also recalled that the actual infrastructure is not able to tolerate significant additions of renewables as they are. There is a tremendous push from ICT, because it's a huge new market. And so it's very interesting because the numbers will be very high. And of course, there are also entrepreneurs that see a new possibility of the market. At the end, this can be a really win-win situation, because the end users will have autonomy, energy savings, a much more central role in the market, capability to trade independently their energy, even in aggregation with other people. The distributor system and aggregators that so far have been looking at this market as a very negative evolution, because they wish to keep the situation as it is, what they know. And this is a tremendous problem also of mixing backgrounds and mentalities that are very far from one from the other. From power systems to ICT, there is a big valley in the middle. Anyway, they will get better exploitation of the electrical infrastructure, extended availability and programmability of distributed generation, participation of end users to generation, storage and management, and higher flexibility, robustness and efficiency. The only thing that these people have to renounce is to control individually every single end user. This cannot be done. So the aggregation of end users to constitute bigger users that enter directly in the market is necessary in order to make this evolution possible. And of course, environment, society, economy will have green energy, citizen participation, more green collars, and so many other advantages. So it's a potentially disruptive new market. But now let's go rapidly to take a look at how this can be done. Do we have the physical capability to manage the energy in this way? And essentially it's a problem of optimum control, and I speak about optimum control of the ELAN, because the ELAN is the basic element of this restructured network, and if we are able to control the ELANs, we can scale up this capability also to aggregation of ELANs, and so constituting a layered new environment. So let's begin from the smart node, this point, what we call energy gateway. Essentially, how it is made. There are, in general, we have some kind of energy sources, can be batteries or energy storage devices, can be photovoltaic systems, can be any other source of energy, wind, whichever you like. These interact through DC to DC converter. This is a power electronics section in a DC stage, and then they bring their energy at the inverter, on the inverter side, and the inverter goes on the grid, interacts with the distribution grid. So essentially we have sources, we have the distribution grid, in the middle we have power electronics that controls the flows of active, reactive power, and also, of course, preserve the energy sources, utilizing the best way. So there is an efficient management, power management here, and interaction with the grid here. Of course, any smart mode will be equipped with a lot of additional instrumentation that is related to metering, synchronization, local control, if we have specific local needs on the source or load side. They will receive and restitute information to the supervisory control of the entire ELAN or microgrid. And then, of course, everything is digital. Then we have synchronization and communication capability to the rest of the world. So essentially this is a node that has a power section and a ICT section. I have to say that these inverters, I'll tell you in a moment, are capable to do everything is needed, even now, everything is needed for actively participating to the game that I discussed before. So in this moment, there are no technological bottlenecks to make what I said before possible. This must be clear. There are no bottlenecks. We already have everything is needed to do this. Unfortunately, they are normally utilized in a different way, or the standards prevent utilization essentially of the power electronic systems to perform as it was needed for implementing ELANs. First of all, these inverters means power converters that transform DC current in AC current, because sources perform in the DC current domain, while electrical grids perform in the AC current domain. In this conversion of energy, in theory, the efficiency is unity, so there is no power dissipation inside, in theory. So essentially, high efficiency devices that transfer the energy from one side to the other of the inverter, but in addition have the capability to decide how to appear on the IC side, on the grid side. So essentially, these inverters can operate as voltage sources or current sources. They can do both of these things. It's not a problem. And this is very important because the standards imposed some kind of operation depending on the situation. So normally, the standards related to renewables in the low voltage side require operation as in the so-called current mode. So these inverters appear on the grid as they were current sources, AC current sources, of phase and amplitude controllable. Okay? There are other situations, for example, in the so-called islanded operation mode, when a portion of the grid is disconnected from the main grid and operates alone, in which at least some of these nodes must operate as voltage references. The inverter is the same, essentially, it's not changing, has both the capabilities. It's the kind of control that is different. So essentially, this, in a very simplified way, when you look at these energy gateways from the AC side, from the grid side, you see or current generators or voltage, or current sources or voltage sources, controllable. This is what an inverter. So without entering the mechanism on how this is made and is possible, this is the result. So at the end, we see the equivalent of loads with the capability to control phase, direction of flow of the power, and amplitude of the currents and or voltages that are impressed in the grid. That's all. This is what power electronics is capable to do. The standards today require that these inverters, most of the standards, simply inject the power in the grid in the form of unity power factor. That means they inject currents that are perfectly in phase with the local voltages. Okay? This is what standards require. The inverters obey the standards. This is the most stupid way to manage the inverters, because in practice the inverters can also manage the phase. And with this trick, that means controlling not only active power is the power corresponding to this operation with voltage and current in phase, but also reactive power that are in quadrature, you can improve dramatically the operation of the grid. But today, since the beginning, it was forbidden, because for distributors, they had to be sure on the operation of these local entities. So they enforced the kind of operation that is functional to transfer the energy produced by the local source in the grid, but is not functional to operate properly the grid. Okay? So this is an additional facility that we can implement easily, because every inverter is capable to do this. If you don't prevent by imposing some different rules, it's capable to do. In practice, every inverter is capable to perform what is called 4-quadrant control. So controlling the active and the reactive power with both polarities. Absorbing power, generating power, injecting power, active and reactive. dynamically. This can be done with a speed of response that is within one cycle of the line frequency. Okay? So these are the capabilities of the inverters. I don't want to investigate further this, but this is what is interesting to understand our discussion. So this was just a preliminary because everything is tremendously simplified, assuming in the analysis of our optimum control that the inverters at the end are current sources or voltage sources, and that's all. It is it's true. It's not a inacceptable simplification. So if we assume that these ELANs will be the candidate infrastructure for the Internet of Energy, of course we need to understand several things. First of all, we have to analyze these mesh architectures if we assume that meshing can be one of the mechanisms to be implemented for improving the operation of the grid. Then we have to implement synergistic and consensual control of every controllable voltage and current source. This must be interpreted. So we have these voltage sources, current sources that are controllable, the inverters, the power electronic systems, the energy gateways, okay? Not necessarily all of them will be available for control, because there will be a choice of the end user to define the limits of participation of the synergistic control game. For example, it may happen that in your house, all the energy that is produced by your source is used by your local loads. In this case, you have no power to make available to the rest of the grid. Okay? Maybe if somebody offers to you a lot of money to give power, okay, you can also make a choice to switch off the washing machine and making power available for a much more profitable game. Okay? But this is a game of consensual control that must be considered also in the approach. Then we wish to provide independent control of the power flow at every grid border section. That is not meaning simultaneous independent control, but depending on the time, selecting which are the priority things. So where we wish to control, because with a limited set of control variables, we cannot impose everything. We have to make a decision what is important, what is not. And then we can, of course, in the view on optimum control, target an optimization of system performances to be defined, what we intend as system performances. That system means global and local. So we have local performances in every single node, and global performances of the ELAN as a whole. And at the end of this, we have also to investigate the feasibility, economical and technical, if there are technological bottlenecks, which are the real functional limits of this, and the operational performance that we can get at the end, which is the market potential. So it's a huge Phasors analysis that must be done before assuming that what I said so far is feasible or not. So there are many aspects to be considered. Here, I simply take care of the feasibility of control of these things, how we can manage microgrid with the limits that I said before, ELAN, sorry. At the end, we have a constrained optimum control problem, and we will see that the solution is found in direct form. This is not only elegant from a mathematical point of view, but makes possible much more faster and robust algorithms for controlling the system. So we have not to use very sophisticated ways to get the solution. We get the solution in direct form. In practice, you will see that every grid variable is a linear function of the control variables. It is a property of the linear grid. And the active and reactive power constraints at grid ports or section, in any branch, can also be expressed in terms of linear function of the control variables. And we will see also that the performance function that we are going to describe will be quadratic function of the control variables. In this way, we have a standard optimization problem that can be solved with the usual approach of Lagrange multipliers. In practice, we will work in the so-called dynamic Phasors approach. This means that we represent the variables in the grid as vectors, Phasors, characterized by phase and amplitude, and these vectors apply to represent essentially the behavior during one cycle. So we don't take care of the instantaneous behavior of the voltages and currents. We simply consider their RMS value within a line period and their average phase within a line period. In this way, we represent the alternating quantities as vectors that during the time change position and amplitude. We have a phase reference that is fixed. Normally we select one of the main points of feeding of the ELAN, where we have the bigger utility connected also, and this is the phase reference. And this is also the reference voltage for the grid. Then, in this way, we can define a direct axis and a quadrature axis. We are speaking on vectors in geometrical terms. If we put the reference voltage on the direct or real axis, on the imaginary or quadrature axis, you get the other component, and you can describe every single voltage or current as a vector in this reference direct and quadrature. The interesting thing is that in low voltage grids of limited size, that means low voltage grids are always limited, because normally a low voltage distribution grid is connected to a supply transformer that is rated for a few hundreds of kilowatts. So essentially, in our ELAN, we will probably have a few tens of users, domestic users, say power below 1 megawatt as a whole. So we are speaking of relatively limited in size and in power systems, and these have the property that is very true for actual systems, that essentially the phase shift of the node voltage from one node voltage to the other in the same grid is very small. They are almost in phase. The phase shift is very limited. This allows to identify the direct component of the currents as currents in phase with the reference voltage and also with the other voltages that are very close in phase. So essentially, when we see a current that is on the direct axis, we call it as active current, and because it is responsible of the transfer of active power. Active power is that is measured by the power metering, is what you pay in the bill. While the current components that are in quadrature compared to this reference are the reactive current that do not generate any average energy flow. Okay? So this is only a convenience, because sometimes we use the term reactive or in place of quadrature, or active in place of direct, because the concept of active reactive power is what is easily understood from people in power systems. While if we speak on orthogonal components, they normally have some misunderstanding in linking these to economical terms. So here we will speak in direct currents are active currents and the energy bill flows, and reactive currents do not generate average energy flow. This is just to utilize, okay, this is an explanation that is not changing so much. Then, our grids are simply described by, in terms of topology, by the incidence matrix. Probably most of you know how this is done. The incidence matrix is an integer matrix in which every row describes one of the branches of the grid. Grid is made by different branches connected in some way, and this incidence matrix is a matrix that is always zero in every line except for the initial node and ending node of that branch. So essentially is a matrix that has a number of rows that is equal to the number of branches constituted the grid, and a number of columns that is equal to the nodes that you have in the grid. And this is essentially the graph, is a mathematical description of the graph of the ELAN of the grid that we are considering. In addition, we can define, since we are in the phasor domain, the impedances related to every single branch. So with the topological description made by this integer incidence matrix and the description of the impedances of every branches, we have a full description of the grid. So only two matrices describe everything. The advantage of this approach, normally this incidence matrix is neglecting the reference node, the complete incidence matrix including also that. But what is important is that based on this definition, we can easily write the Kirchhoff equations that are essentially the basic equations that relate currents and voltages in the grid. So essentially you see that the voltage equations in the grid relate simply the voltages across every single branch in the grid and with the voltages in the nodes of the grids. And the same for the currents. So essentially with this information related to the topology of the grid, we can relate in direct form the node currents to the branch currents and the node voltages to the branch voltages. Okay, these are the this is the description of the grid in terms of Kirchhoff equation. In radial grids, the usual distribution grids, the matrix, the incidence matrix is square and invertible. In measured grids, this is not true. So the first development that is needed is to generate the inverse equations that relate, in this case, you see, the node currents to the branch currents, the branch voltages to the node currents, to have a set of equations that allow to switch from node currents to branch currents and vice versa. So this is easily done, are simple computation. At the end you see that we have equations that relate node currents to branch currents in direct and inverse form, node voltages to branch voltages in direct and inverse form. The relation between voltages and currents is dominated by this matrix Y, that is the node admittance matrix. Sorry, these are terms that people in power systems use. Normally, I don't know if you need, we can slow down here, but I believe they are simply description. And so essentially, with the definition of these matrices, with this matrix B that is not the inverse of the incidence matrix, but this is the pseudo-inverse of the incidence matrix, we have a full description of the grid. In the sense we can relate currents in branches and in the nodes, voltages in branches and nodes, currents with the voltages in the nodes, and voltages in so all possible combinations. So we have a full description of the grid in terms of linear equations. That is easy. Then we have, this is a general description of the topology of the grid. Important thing is that with the approach that I'm going to present, these matrices are computed only once. They have to be changed only if you have changes in the grid. In the topology or in the impedances. By the way, these are the impedances of the branch, not of the loads. Okay, so this is really related to the distribution grid. Only if you change the distribution grid, you have to compute again. This, but normally this is not happening. You have a distribution grid, then you connect the loads, sources of various kinds, but the grid remains the same. Anyway, in case of changes in the grid, if you remove one branch, for example, you have to readapt these matrices. Then another point is to identify and classify the type of nodes, because essentially in the grid at this point we can have three types of nodes. The nodes where we have simple loads, okay, the loads connected there, and the loads, by the way, are normally represented in low voltage lines as constant current loads, in the sense that normally the loads take constant power, but constant power, since the voltage is nearly constant, means constant voltage. So in the first assumption, within one line period, within 10 milliseconds, we can assume that the loads are constant. In the next cycle, can change value. Okay. Then we can have inverters performing as voltage sources. That means we have sources there, energy storage devices, And this characteristic of being voltage sources can be due to the fact that we have an inverter acting as a voltage source, or a standard feeding of the grid, so transformer connection to the grid, to the main grid. This is a voltage source. So essentially here we have the point of common coupling with the utilities that normally feed voltages, or inverters operating in the voltage mode. Then we have other nodes that operate as current sources that are normally the distributed energy sources interfaced by inverters that are enforced by the regulations to operate as current sources. With this definition, this is important because these rules can change during the time. So we can express the currents in the voltage nodes. These IG are the currents in the voltage nodes. The currents in the currents node, you see here, are called US. The currents in the load are simply U, because loads and current sources are essentially constituting what we call the user node system. They are all current sources. So at this point, we can define this matrix simply to extract from the total set of current those that are interesting for us. Currents in the voltage sources, voltage in the voltage sources, current in the user nodes, voltage in the user nodes. So by defining these matrices that are simply matrices made by integer matrix with coefficient 0 or 1, we extract from the total currents, for example, the currents in the generator nodes, or we extract from the total currents the currents in the user node. This is important, the use of this matrix is important because the role of the various nodes can change during the time. So we can have that in some period of operation, one node operates as a voltage source, and later on, in another moment, will become a current source. So we switch from this community of currents flowing in voltage source to this community of current fed by current sources. The interesting thing is that in order to change this classification, we can simply change these matrices. All the other matrices that are related to the topology will remain the same. So at the end, we will adapt the actual operation of the grid by simply multiplying by integer matrices instead of changing the entire system of matrices that are related to topology and impedances. This is a tricky point that is completely stupid, of course, but allows to make very simple algorithms, very fast algorithms, to adapt to the situation that can be changed during the time. So then we can define at this point the input-output equation, because we normally define as outputs the non-impressed variables. So the outputs are the currents in the voltage generators and the voltages on the current generators, or in generally in the user nodes that are fed by current sources. So we have that the input variables are the voltages fed by the voltage source and the currents fed by the current source, and the output variables are the opposite, so the currents in the voltage source and the voltages in the current source. Why? And all this is the transfer matrix is obtained, as you see, by simply multiplying the fixed node admission matrix by matrices that are simply integer numbers. So this kind of transformation is very quick, very easy, and allows us to change during the time the definition of the various nodes, what a single node is doing. It's simply a way to describe easily and to adapt quickly the equations to the actual operation of the grid, or better, to the actual attitude of the distributed sources to operate as pure loads, to inject power, to perform as voltage sources, or to perform as current sources. So we can adapt all the situation. Our actual control variables are, of course, the controllable voltage components at the voltage nodes, direct or quadrature components, not necessarily both of them, because if you consider a tap changer, a transformer with tap changers, essentially is a transformer in which you can adapt the output voltage, but only on the direct axis. So essentially, reduce the number of turns that you get in the secondary side of the transformer. You can adapt the voltage, but this is not quick and cannot regulate in both axes, only in one. While usual inverters can control in both axes, direct and quadrature. The same is controllable current components. So essentially, we have that a subset of the total voltage sources will have controllable component, and a subset of total current sources will have controllable current component. These are the control variables. Okay? So in a system with, say, 100 nodes with 50 sources, not necessarily all 50 sources will be able to provide control of the voltage or control of the current. This depends on how the inverter is made, how the control is capable to operate, and so on. So we can adapt to this. We have to be capable to adapt to this. In any case, we can easily write, so at this point we define as input variable the controllable voltages on the direct axis, the controllable voltages on the quadrature axis, the controllable currents on the active currents, and controllable currents on the quadrature axis, that means reactive currents. So these are the sets of control variables. And we can write all input and output variables in general as a function of this one, including the branch currents. So essentially, we have a set of equations that are very easy to determine, that depend on the topology of the grid, on the impedances on the line, and on the attitude of the nodes to operate in a way or another way. Okay? Sorry, it's very annoying, this part, but I hope quickly to arrive at the end. At the end, we have a linear system of equations in which we can relate all output variables to the input variable, and these terms y0 is simply the situation that we have when all control variables are 0. So the grid is normally operating anyway, even if all the inverters are switched off, the grid is fed by the utility, and so there is a level of operation that is not 0, even if we don't have any control variable. So we can define, this is a constant matrix that depends on the previous ones, it's very simple. And then we can think about the objective of the control. So we have a description so far of input and output variables. And what about the objective of optimum control? In general, we have defined a cost function that takes into account different aspects. Of course, there are weight factors that allow to consider or to weight differently those aspects. First of all, the losses. In a general distribution grid, we have two kinds of losses. One is the distribution losses, that means the losses that are due to the fact that the currents flow in the lines. They find a resistance, the equivalent resistance, and so they are source of losses. Then we have the conversion losses, because power electronics is not with unity efficiency, so we have losses also there. So one part of the function, cost function to be minimized is related to the losses. This is a factor that's normally important, because reducing the losses increases the efficiency, reduces the energy bill normally, essentially, and is also a factor that determines the proper operation of the grid. You know that any physical system tends to operate with the minimum energy. Any electrical system tends to operate, the best way to operate an electrical system with minimum losses, with minimum distribution losses. This means that the distribution of the currents is the best one in terms of utilization of the distribution system. Other factor is the stress. Of course, in our cost function, we have to include also the stresses that can appear in our system. And these stresses can be the current stresses in the feeders, because every feeder, every line is sized for a specific current flowing there. And if you exceed this current, or you arrive very close to the nominal current, you have a heating phenomenon, and utilization of that cable or that line can be improper. So can generate in the long term faults or defects and so on. So the current stress in the feeders is one factor. The power stress of the source is the same, because if you have to share the power the load power among different sources, the best way is not to stress some of the sources close to the maximum and have the other ones inutilized. The best thing is to proportion the power sharing in order to have possibly a proper stressing of the sources for every one of them. Then we have also the inverters are stressed by the fact that they manage current. So the fact that an inverter is providing a reactive current that is not giving contribution to the transfer of energy, but can help operation of the grid, creates additional losses, because anyway, in any case, is additional current flowing in the inverter. So also the inverter must be taken into account in terms of thermal stresses, essentially. You cannot create a situation in which you can have failures due to overstressing of the sources, of the inverters, of the feeders. And last but not least, another aspect to be optimized is the voltage deviation. That means the stability of the voltage profiles. The ideal situation is that in which all nodes in the grid have the nominal voltage. This voltage in practice can go up and down a little bit, but there are limits within these plus or minus 5%, 10%. These are the limits that in some way relate to the quality of the power that you are feeding to the loads. So there are several aspects, and we can define a cost function that with proper weights can consider all these aspects, depending which is more important for your specific application or in a specific moment. Okay? All these functions can be expressed in relative form, first of all, to make them comparable with each other, and in quadratic form compared to the depending on the control variable. So at the end, our cost function can assume a form of this type. Of course, there are many annoying passages in the middle, but this is the result. Then, so we have a cost function to be minimized. We have equations that give all variables of the system as a function of the control variables. Then we have constraints. We have a set of constraints that depend on what we call phase constraints. That means constraints related to any single phase. You know that distribution systems are normally three-phase. Even in low voltage, in your house you will have only one of these phase with ground, but the system is globally three-phase, and another house will have another phase with the ground. So there are constraints that apply to one single phase, and these are normally related to active or reactive currents or power absorbed at specific source nodes. This, for example, to ensure some power exchange at the point of common coupling with the utility, demand response. Okay? Or it can be the problem of branch constraints. We wish to have the current flowing in a branch to go to zero because the branch is faulty. We wish to have active isolation at the branch. Or we have a branch that is overstressed. We wish to divert the current to other paths. So in this way, this kind of constraints allow us to say, okay, we wish the power to flow in this way. This section, this section, this section normally is not needed to follow the current in every single branch, because you can simply assign the current in some critical branches, and then everything follows automatically. But anyway, we can essentially impose currents or power at given nodes of the grid or in given branches. These are constraints. We say, for example, at this moment we wish to exchange 100 kilowatts with a utility, because the utility is asking us 100 kilowatts, we wish to convey 100 kilowatts, maybe in phase one, not necessarily in all three phases. Okay? These constraints essentially are constraints in terms of currents, and simply can be expressed in terms of active currents that have to follow some given references, or reactive currents, both in nodes or in branches. This can be linearly expressed in terms of the control variables, and so take this form. Then we have other boundaries. It's called interface constraints, because the currents flowing in the nodes or in the lines can be constrained, for example, by the type of connection. We can connect the loads as single-phase load, line to neutral, line to line, or three-phase loads that can coexist in the same grid, can be Y connected, Y with neutral, delta connected. So this imposes a series of boundaries, of constraints in the various currents. Y connection means that the sum of the three currents in three phases must be 0, for example. Line-to-line connection on single-phase load means that there is one phase that is not involved, so 0 current, and the other two will have currents that are one the opposite of the other, because the current enters from one phase and goes the other one. So these are connection constraints, and then we may be enforced to include constraints on the symmetry, because in some section of the network we can be required to offer what is called balanced operation. That means symmetrical. All three phases must provide the same active and reactive power. These are other kinds of constraints. So this is again linear in terms of the control variables. So at the end you have constraints that can be expressed in linear form. Of course, obtaining these matrices requires some kind of work, but at the end we can implement in this way the system equations, the boundaries, the constraints of operation, and the cost function in a way that can be solved in direct form by Lagrange multipliers. In practice, given these matrices, we can find the solution. So take a look at the solution. At the end, we have here we have one inversion and multiplication of matrices. These matrices are essentially generated by simple operation, because are equations or simple multiplication of constant matrices. So we have one inversion here. Is the only real, another inversion here. So the algorithm of solution requires two inversion of matrices, okay, that have the size of the number of variables. So essentially, it's a very simple algorithm. We have to prepare all these matrices, but we never change the main matrices described in the grid. We adapt to the situation by these identifiers that I have shown before, and at the end we have to invert only two matrices to go directly on the optimal solution. So there is some preliminary work in that, but at the end we can manage the problem, because here probably is not clear, but here we have been putting everything in the same problem. So the solution that we find, the control variables we find here, solve at the same time all the constraints that we have been putting in the problem, and minimizes the cost function. So the question that you asked before, communication or no, this is not in a single shot, while minimizing the cost function.
It doesn't want to comment, but I will comment. So the optimization aspect here on my left-hand side says, this is very nice because the problem is simple. It's a convex quadratic problem problem, so you should know how to solve it digitally, according to the student. And also you have only equality constraints, which make it even faster. I would add also that this is, by looking at that, it could be easily also implementable in a distributed manner. For example, this is a convex optimization. It could be possible to distribute it using ADMM, for example. If you find a way to build, to write down the objective function in a way that you can separate that.
Probably, yes.
And write it as a sum of specific function, a specific cost function for each element that control, each control element.
Yeah. In this vision, obviously not, we imagine to have a supervisor of the ELAN that in some way makes this computation. But probably the problem can be reformulated in order to allow for distributed solution. I believe the control people are definitely capable to do this, because it's one of the main evolution of control in the last years was to devolve centralized control function into a distributed domain. I believe so. Our approach was and is also relatively reasonable, because the idea to have one central controller for ELN is not so strange, because at the end this central controller will manage maximum 100 distributed agents. Is not huge problem, but probably can be distributed.
My concern is then, I'm just looking forward, if I wanted to, I would like to implement this distributed, probably I have one idea of how we can rewrite it's just a rewriting the problem, the formulation in a way that is
Absolutely.
amenable to distributed.
Absolutely.
But then there is another problem. When you, usually, as far as I know, when you implement a distributed optimization, you make a decision which is local, and every node is making a local decision, and this decision is implemented. So basically, you're changing, you're steering a little bit the voltage, you're steering a little bit the current. You implement it. So it's not just simulation. You're implementing it. So this has a consequence in terms of network operating point. And then iteratively, after what I know is that usually if you run it properly, after a few time steps, a few iterations, the whole thing will converge to this exact offline output.
Yeah.
So I'm wondering now, this is simple, so you have all of it, you send it to a central controller, the central controller computes, and then we'll send back the solution to the controllers, the local controllers. They implement it, and boom, you have the solution implemented there. If you do it distributedly, is there any risk of adapting?
You have some conversion time, of course.
Is there any risk that I'm adapting a little bit, but it's not exact? I mean, there is an iteration process that will take 50 to 70 to 100 times long, depending on the type of problem that you have. Is that risky?
Yeah. No. I believe that this will work perfectly, for a simple reason, that these kind of systems, in this kind of system, you do not have problems of instabilities due to the local operation of the system. In the sense that even if you leave every local system working alone, you will not have the optimization. Probably you will not comply with all the constraints, but the system will work perfectly. So the electrical grids today work perfectly without introducing all these things. So if you imagine a way, the problem is which are the markers that you wish to take, and which is the kind of information that must be exchanged between the nodes in order to have a distributed control that converges to the same point. This has to be studied, but I'm sure that the system, there are no risk of instability, because locally every system will work properly. And at least until you are connected to the grid is big enough to ensure that the operation is correct. In islanded operation, the problem can be much more difficult, because there, if you have not a complete vision on the system and you rely on consequent communication, you can reach a situation of instabilities. Until you are connected to the grid, I don't see any problem, because the system will work anyway. So your problem is to converge to an optimum or quasi-optimum situation, of course, in a longer time.
You're telling us that the mains, so the power grid, is covering our back, basically.
The mains is covering everything you need, by definition. Of course, in this way, in one life cycle, you adapt everything is needed to perform the new. You can follow references from one life cycle to the other. In the other case, you will need more time.
In terms of security, this is just for you to know, because I'm also doing research in this. It's not, of course, power grid, but we are using the same approach, distributed approaches. In terms of security, as far as I understand, it is considered safer to act distributedly, because if you have a central controller that you can hack and you can change and produce something really bad for the network, there in the distributed way, each one is making a decision which is local, is a tiny decision, and the ensemble of all the decisions that are made by the whole network is creating what you're looking for. So it's going to the final solution. But individually, a single node is not aware of the whole network, doesn't know what the other nodes are doing, it's just reacting to local interaction. And that is, in terms of security, is you need to compromise. If you compromise a single node, probably you have a solution that is not very efficient there locally, but the rest of the network will be good. So
Absolutely.
you need to compromise many nodes in order to impact heavily the network. So this is usually what they say is a benefit for a distributed approach, because the overall solution is not written anywhere. So it's going to be distributed, and every node is a limited, let's say, knowledge of the whole problem.
Yeah.
Correct, Ron?
Yes, sure.
Mm-hmm. Now this is a very important and tricky point. By the way, here we have some help, because most of the matrices that we are looking at here are computed only once. This could be available around, and so this helps. So the quantity of computation that you have to develop locally can be relatively limited. So if we are able to decompose the total problem into sections that relate to the single nodes, taking part that there will be an initial phase in which the main data will be constructed and distributed to everybody, and this construction can be done in parallel by the different nodes, I have no doubt in that. If we are able to reformulate the problem, consider that most of the work is done only once, probably this can help in getting both the robustness and the efficiency of a centralized situation and the advantages of delocalized control and computation. So this is a point, because this is a starting point, but how to implement this, I believe, can be discussed much more deeply looking at the real situation. For sure, having a single supervisor is the natural approach in a problem that is limited by definition, but the distribution of responsibility with the other distributed nodes, distributed agents, I believe could be a very interesting approach. And the real testing point will be in this landed operation anyway, because their reaction times must be much more faster, because the power balance must be completed within the network, within the local network. Yeah.
In distributed control, how important would the synchronization of the the individual interactions be for the stability or convergence of the power system?
Yeah, this is one of the most important things. I didn't speak about this, but we have made a lot of work in that. The problem of synchronizing all the nodes is a big problem and can generate instabilities. So the trick that we found out is very effective is to distribute the commands in terms of power, active and reactive. Because the concept of power is, first of all, is conservative. So if you add the power generator in various nodes, that sum is independent of the phase of the local voltages. Okay, power is a conservative quantity. And power is something that is inherently resolved in terms of synchronization locally. So if I ask you 100 kilowatt, you will inject the current that gives 100 kilowatt, considering the voltage that you have in your node. Okay, so if we express our constraints in terms of currents, this inherently requires for synchronization, because I express this boundary, these constraints with, in my mind, a specific reference, phase reference. If I express the boundaries in terms of active and reactive power, this is not requiring any synchronization. So the tricky point here is that this supervisory action then will generate commands to the distributed units in terms of power requests, not current requests. This prevents any need for synchronization. We have developed a theory that is so-called power-based control that exactly utilizes this concept. In any case, you distribute the control, you express the control commands in terms of power terms, never current terms or voltage terms. Because synchronization can be complex also because the phase difference here are very minimal. But if you look at synchronization, you cannot be considered that they are zero. You have to really synchronize locally. And so synchronizing small parts of 1 degree is not very easy. The phase displacement is very limited in voltages.
So is it the same as like, you know, all the nodes are kind of tweaking their parameters, and you know, then if suppose, you know, 2 of the nodes, they change their parameters at the same time, or, you know, this changes its parameters first and this second?
Who knows?
It doesn't. But would that have an impact?
Now, when you are in a real grid, the loads change in from one period to the other. You cannot prevent that. Your refrigerator, in some moment have the pump working, in a moment not, and the washing machine is in different phases of operation. So the loads changes continuously. The source is the same, because you have a photovoltaic system and you have a cloudy situation in which the clouds go back and forth. You can have a reduction of 30% in half a minute. So the system is continuously moving. So essentially the problem is that you have to make a measurement on the basis of 1 line cycle. So the updates must be a reasonable time is 1 line cycle. That means 20 milliseconds. Or if you really wish to go fast, half line cycle, 10 milliseconds. You have to update all these numbers. You feed these numbers to the controller. The controller updates the matrices that depend on that without creating new big matrices regarding topology. This is not changing, nor impedances, and adapts for the new. But you cannot make any forecast in that. What you can forecast is in negotiation with the utility. If the utility has a daily profile of power and requires you to provide that power along the day, you can arrange yourself with the energy storage and so on to satisfy this requirement. But locally it's very difficult to make predictions.
So if I got it right, so you are instantaneously optimize the system?
Yeah. Yeah, with the delay time that is 1 line period.
Okay.
20 milliseconds. Every 20 milliseconds you repeat the optimization. But 20 milliseconds, since the algorithm is simple, 20 milliseconds is a reasonable time to implement that and to communicate the data. But 20 milliseconds is a very short time for electrical systems. Normally they react in terms that are seconds. So we are here proposing a situation that is much more fast than normally happens in the electrical grids.
You just mentioned about synchronization in the energy level, in the energy layer. Do you think that we have obviously very fast communication live?
Yeah, the mic normally serves.
So we have very fast wireless communication link. Always syncs to our base node. Do you think that by having a very precise timing in like a microsecond timing, through the wireless communication, can it improve the synchronization in the energy level?
No. Frankly speaking, not, because the fast phenomena in the energy level are all inside the inverters. Inverters can break, can have a shutdown in 2 microseconds. But and every protection system is inside. So this self-protected is not. You cannot protect an inverter by sending communication somewhere. No, is completely done inside. So the inverter really, when you look at this from the grid, you see a current source or a voltage source. That's all, with perfectly shaped waveforms. So really, the communication we are speaking here are communication that must provide performance in the order of tens of milliseconds. Managing rapid phenomena, but even in a network, in an electrical network, a microsecond is only the atmospheric phenomena have these times. but the electrical phenomena normally run in the order of few or more or many line periods. So introducing communication capable to manage phenomena of 1 microsecond can be nice if you have to exchange lots of data, but are not needed, I believe, to run the system. Consider that a circuit breaker, that is the main institutional protecting system for electrical networks, has a typical opening time of 20 milliseconds if you are lucky, but can be hundreds of milliseconds, depending on how it's done. So really, these are the times of electrical network. I would not worry too much on having fast communication to manage electrical phenomena in electrical distribution grids. Maybe you have a different opinion?
No, I was going to ask a question. Yes, I wanted to know if you had a chance to experiment with all this theory on actual hardware, maybe in your lab, trying to implement a demo with a small scale. Is that something you did or are looking?
Yeah, we have an experimental microgrid in our laboratory, and we have been testing with a real-time simulation system, so we can simulate what we do not have available. We have a PV system, we have batteries, and so on. Really, for this kind of, and so we have been working essentially on power-based control, distributed control, this thing. This approach is relatively new. For the moment, we have made a simulation environment in MATLAB that is capable to manage all these things, and in fact, the last part of my presentation is relating to this one. So we have been trying to develop, first of all, the theoretical. All these matrices that we have seen in some way must be computed and depend on the parameters and so on. And then we have been developing a MATLAB code.
Yeah, 5 minutes left.
Yeah, okay, but we have finished, in which we can select almost everything. I'll show you an example. So we can select the network architecture, the ratings of every component. We can select the types, connection, power ratings, controllability, and constraints for every element in the network. We can define daily profiles of absorption or production depending on the loads and sources. We can select the cost function, and we return a complete description of the grid operation. That means currents and voltages at every nodes. We can group the nodes in categories, or whichever is more convenient for the user. And here I have an example of a network. Okay, this is a typical network that we have. This is, imagine a city quarter. Every node here is a group of 3 houses, with some of them equipped with photovoltaic, some not. These are the main distribution lines. We have 2 utilities connected to divert the power from one to the other. These are the main feeders. We have, imagine, blocks of houses, 30 houses per line, 3 of them. So in total we have 71 branches and 68 nodes. And so it's a meshed grid. In fact, a normal distribution grid would not have these branches here, because a typical is flowing with lines this way, so it's radial. We have added a limited number of additional branches to mesh the grid. And so at the end we have 68 loads sources of various power levels. Here is a commercial area with shops and workshops with higher power installed. These are various kinds of houses. So essentially you can define the type of cables that you use for the feeders. You can have categories of loads, because normally some of them are repetitive, so typical photovoltaic system for domestic application. You can define the characteristic of the main power supply, so the medium voltage step-down transformers from the line, the characteristic of all the inverters that you have. And at the end you get, this is just the summary table that gives you a lot of information on the operation of the grid, but then you, for every branch, every node, and every group of nodes or branches as you have been decided to group them, you have information on power, currents, stresses, and so on. So for the moment, it's just a simulation, but includes the algorithm that implemented in our microgrid or in any other experimental facility could really try to verify the operation of this one. So essentially this is what we have done, and wish to conclude here. Future work, this is the point where we are. Of course, we will have to, this is an important point that we are in this moment developing. A problem that I did mention, given the distribution grid, where to locate the energy storage devices and how big. This is a big issue because today, this is a point today under discussion, because we have the grids, we have the distributed energy sources, renewable, but everybody is trying to understand which is the best way to use energy storage. Small distributed, bigger concentrated, where to locate them, which are the advantages. This method allows to analyze this. Then we wish to go also to analyze the so-called silent grids, where not all the nodes communicate, only a part of them. Maybe only the active nodes where you have sources, but the passive nodes with standard loads maybe are not equipped to communicate, to inform. And then implementation of real-time control algorithms, so transform this formulation into real algorithms, and then extend the application not only to usual distribution grid, but other environments that are very challenging, all-electric ship, aircraft, plug-in electrical vehicles, because these are all grids where the operation of distributed sources is very interesting. Okay, in the end, looking in the crystal ball, and then is the real end of my presentation, is a question: will this traditional oligarchic electric market eventually evolve to a more democratic arrangement? This is the history. This is the real question, this one, because there is a tremendous opposition to go in this direction. There's a tremendous push to go in this direction, a tremendous opposition against this move. And Europe said in 1 decade we have to do that. Who knows? Let's see what happens for the moment. Thank you. Okay. Of course, I'm here if you have any other questions.
Can you just summarize if there are some challenges for the communication part of this?
Yeah, essentially communication. At the end, we will have a proliferation of data because consider the situation. I said that we have to update the situation every 10 milliseconds. But how many data will have to be exchanged in a safe way in order to get the results? And then, of course, the real application and the real demand for the telecommunication system will depend on what the telecommunication system will be capable to do. So whichever are the performance that the communication, safe communication, secure and so on, can provide, I believe will be used. Because the proliferation of functions here, we just look at the energy level, that is the physical, the hard physical system. But above that, all the services that will manage these things, the interaction between subsystems, the interaction with the upper level, the negotiation, how much communication capability we require. We are going rapidly in the big data domain there, because the quantity, imagine to be an aggregator that collects 10,000 users that are maybe aggregated in other communities and has to manage. I believe there you will have a tremendous quantity. Here we need, for sure, big level of security of data. Not only for running the control, but because this is an economical problem. Entering the system in some way, being able to modify the data to simply intercept the data while we're moving can create a big economical problem. So inherently, I'm sure that the demand for communication will increase, because remember, the system is generally slow, the electrical system, but the inverters are not slow. The inverters are much faster. So if in a future envisionment of new control, direct communication of inverters to improve some kind of performance that allow to react to fast dynamics, or to manage properly the operation in the islanded mode. So when a group of users is alone, is not connected to the grid, this will require much more faster communication. So I don't see the limit in that. With this approach, this is the basic approach. But in future, managing islands more and more complex, that means systems that inherently, instantaneously compensate generated and consumed power in order to have the power balance. This will be a much more intriguing and challenging world for communication.
But as you answered to Sohail, that the the grid reacts on a larger scale.
Mm-hmm.
So improving the speed of the communication is not really a very big, very critical challenge. So would you say that security and quantity of data is the more pressing, more critical?
At the level of energy, the level of control of energy, security, and of course capability to manage the data that are needed for the.
When he's talking about islanded mode, it's not what it is.
No, islanded mode is.
It's a different thing.
Okay. No, I can show you what intend.
Detached from the power grid. You have your island, which is an autonomous system detached from the power grid. In that case, you cannot any longer count on this Y0 that you have over there. So you don't have a zero situation. So the power grid is basically over your back to do something. The power grid is stabilizing the system. If you are off grid, so this island.
Imagine that this one is not connected to the main grid. So we have 100 houses alone. They have to create their own voltage to keep up the grid, and at this point you have to balance the power consumed and generated. There's no way. You can take advantage of energy storage, of course, to balance temporarily, but at the end you must find the balance inside. Well, if you are in the big world, of course, you can return energy to the grid, you can get energy. The grid provides you, in theory, what is needed, or accepts what you are selling. But when you are alone, it's like being on a small boat in the middle of the sea, or being connected to a big ship in front of you. So it's a big difference. So this will be the real challenge. And is not impractical, it's very practical, because there are islands. There are areas, many areas on the world that do not have a reliable electrical distribution. If you think to the hospitals in some areas of countries where there is not, like in Europe, a very strong grid, they have to provide this big power locally, and there must be a local compensation. This will be a big challenge. And in this case, everything must be much more fast, because you have to adapt to the quick variations of the load by providing quick variations of the sources. At this point, the game is completely different.
Sorry, I really appreciate the talk and the participation of everybody, but we are really late. So
I'm sorry for that. No, I am the responsible.
Really nice. No, that's really nice, because there is such big participation, so it's something that I'm really happy of it. But we have to go, because we have another, so I'm sorry to...
No, sorry. Sorry for taking so much time. Thanks for being here. And
thank you again.
Thank you.